time here. All right, we got to talk through speeding up like realistically a 4-hour exercise to about 20 minutes, and a pretty good plan, but we got to talk it through. Turn the air conditioner on here so that the phone won't overheat. Thanks, Android. Okay, the topic is using AI for test engineering, and specifically for diffing circuit boards. A diff function, right? Diff in software just means line for line, compare this to that. And if there's even, the tiniest difference, even an invisible character like a tab, they won't match. You can get more advanced diff that will say functional diff, right? Like, does this line functionally do the same as that line? Even if it has different spacing or different whatever, right? And then you can get really smart diff that says, will this method have a transfer function which is the same as that method? And at each step of going higher level, it becomes more complicated. The trivial case solves out, but you'll find that there's other dependencies. Like if you change all the names, sure, functionally it'll be the same, but it will break the code. So you end up needing deeper and deeper permutations of search in order to perform a diff. This is kind of the baseline we're starting from. If you're not following that, you're not going to follow the next thing we do. Remember, I am comfortable with compilers, and so we'll be thinking of PCBAs in terms of compiling. Now, there's a keystone that people don't realize is that any kind of, let's call it an IDE, used for laying out a circuit board, represents everything in text, ultimately. You can think of it that way. I think most people know that SPICE models are in text. You can write down a SPICE model. It's just a bunch of fields with a bunch of numbers. You got some calculations you can do, and this will cause a simulation to calculate your basic electrical engineering for inductance and capacitance and rise time and fall time. And you can represent things. Well, it's much simpler in a PCB layout. You have to ignore layers to get down to what it really is. So you ignore the 3D rendering. That is totally and completely separate, and it's a different module. And then you get down to the actual copper, all right? You might say you can't diff that, it can infinitely move. That's right, it can. So you ignore the actual copper, all right? You pay attention only to the rules on that copper. It must have this much standoff. It must be this width and this thickness. It must be these balanced pairs, right? Net rules. So an arbitrary PCB board has arbitrary dimensions, a couple inches by, 2 inches by 4 inches, whatever. It has connectors on it, always does. And a connector could be a stacking header, it could be, a high pin IO, it could be a micro connector, it could be a big connector, it could be a solder pad, it could be a through hole, it could be many things. So we also have components. Every component is represented by a model with a schematic symbol, a footprint with pin numbers, and a mapping between those. All right. Now we've got a spreadsheet, and I'm going to describe to you a hybrid method using some AI. It can be solved brute force. I have solved it brute force. This is the time we want to cut out. This is the human time. So we're going to be opening a spreadsheet. So to zoom you out, we have a PCB board sitting on the table. It has connectors all around it. It has parts all over it. These parts and the connectors are tied together via traces. Those are called nets, right? There's a net list. You can click on any part and say it's a connector and it has 6 pins. Each one of those pins is hooked up to one and only one net. There's a rule you have to know. You can't have 2 nets connected together. That wouldn't be a net. All right, that'd be 2 nets put together into one net. So they're electrically the same. So a net is one single electrical path that rings out on the ohm meter. It could go through a jumper and become a different net. You'll be careful for shit like that, but it's pretty uncommon. If it flips through to different layers of the board via a via, it's still the same net. All right. Now we have something called test points. These are EING pads. They're gold pads, a millimeter, or 2 in diameter, and they're sitting on the nets. So what we want to do is a first step of determining our percent coverage. What we're going to make is an incoming inspection readiness for test automation script, and we're going to call APIs for we're going to put some trust into AI, and we're going to jump the human aspect in the gap using API calls. And it's very, very simple, and it shouldn't fail. So first task, I've done this in Eagle and I've done this in KiCad, which are open source layout programs. They're Python friendly and they expose everything for community testing. So we're going to be doing it against any arbitrary layout program. Let's just pick Altium because everybody uses it. So the program has to facilitate import and export, and you got to dig around for that. So the first thing we do is we're going to highlight all of the connectors. All right, say there's 5 of them. Click them, bop, 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 right? Now we need to export a table of those. And that's going to look like a connector and 6 pins, a connector and 8 pins, a connector and 2 pins, a connector and 5 pins. Those are ordered, those are numbered. If the connector doesn't have pin numbers, it wasn't a good design. All connectors have pin numbers, they all have a pin 1, they all have an orientation. Each one of those pins is either connected to a net or it's not. If it's not, we just put null right there, something that represents nothing, that won't be confused. Traditional null in all caps will be great. We can ignore those. Electrically, they're not connected to anything. We have, and the exact formatting is important. So just picture a spreadsheet, and the first row, you're going to be over a few columns, and it's going to say that it's going to have the first column is the name of the connector, and that's repeating. It'll be like connector 1, connector 1, connector 1, connector 1, and then J1, J1, and then J2, 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 and then J3, J3, right? Doesn't matter how the program spits it out, we run a parse against it to sort it. Next column over has the pin numbers associated with those. 1, 2, 3, 4, 5, 6. I would prefer that they are ordered. If there's multiple rows, you have to be careful. Some of those might be as high as 90 pins, something like that. The next row over is the net those are connected to, right? That's in the text, in the bowels of the PCBA IDE. The net, the electrical net, all right? The next column over, pause. All right, restart the activity in a different part of the spreadsheet. We're gonna go and we're gonna do a search for everything named TP, test point. And we're gonna pull all those out. We're gonna drop them down in a spreadsheet ordered. Test point 1, 2, 3, 5, 6, 7, 8, 12, 15, 16, right? They're not necessarily ordered. In fact, the names are arbitrary and they only need to be leading with a TP, and they only need to be unique. And so each one of those is attached to a net. There's no such thing as a floating test point. All right, if one is floating, you have an immediate error. Test points don't float. Some of them might be on ground, some of them might be on power, some of them might be on various rails, some of them might be on connector points, some of them might be on random parts of the circuit of interest. Can you hear? Now we have a spreadsheet. Over on the left somewhere, we have a list of test points going down, and to the right of that, the net they touch. They don't touch multiple nets. They just touch one net. On the right, we have a list of connector names, followed by a list of the pins, followed by the list of the nets. Now is where the human would come in and play fucking mix and match. There's 200 of them. It could take 15 minutes, it could take a half an hour, who knows? We're gonna line those up. We're gonna transfer, we're gonna run down the list of test points, find the net name that matches, and move that test point over to the right of the columns of connector pins. Now I've done this in the past, just brute force, and it's a small O, right? It's not big O. It's only on the order of 100. So you can do a brute force pass. You start with the first test point in the list, and you look at its net name, and it's a text perfect 1-for-1 match, and then you search the column of connectors. Now it might show up in multiple spots. Example of that is ground. You can work it either way. You're going to have some duplication. So since the connectors are physical and unique spots, let's go ahead and have the test points duplicate. So anywhere where you get a text match on net name, you write down that test point name. And so you might, depends on how you want to parse it, you might have test point 1, comma, test point 5, comma, test point 6. Or you might have some maximum number of columns, like 10 columns, and just let them populate, left to right. I can't remember how I did it last time, but it doesn't really matter. It just depends on how good your parser is and how much of a parse you want to do. The easy path is just to keep bumping to the right one column for each match and have some maximum number like 50. You never hit that. That's where bugs come from. Okay, so now we have a mapping of connector pins to test points. Remember, test points are little gold pads in a PCB. And what we make is a test fixture, which is a bunch of gold pins that reach out and touch those points. So if we want to emulate next assembly, which would be something that plugs into a connector, then we must touch a minimum viable product number of the pins on the connector to do that. Okay? Ground, power, high speed signal, digital IOs, analog signal, doesn't matter to me. We have another column to go. This part, we will leap the gap with mat in the middle, but later on, when net rules are better defined, you can actually parse this out. So for every single one of these net lists, hold on, go. You have net rules, all right? When I lay out the boards, I set it up for myself for tests, so it's a little more obvious, but there are 4 basic types. And I'll put a 5th one in there as a placeholder in case I haven't thunk of it yet. I can barely turn my fucking head. Okay, the net list might have rules, or it does have rules, or it should have rules. The first one is its high voltage rule. How much standoff is required around this net, right, for high voltage things? Might be 1/10 of an inch. You have to respect that. The next thing is how wide must that net be? This is if you auto route or if you start drawing. What's the default? That's for high current. Okay, it might be 50 mils wide, and we add the attribute of leave that as an unmasked trace because it might be 9 amps or 10 amps, and I might need to just run a bead of solder along it to beef it up, or I might need to run a 2-ounce board, something like that. The next thing is high speed. This would be very easy to identify anything that's balanced line or just do this part as a human because it's the big O, the order is on order of 5 or 10. You just look at it, dude. You're like, okay, that's a USB connector, that's high speed. Okay, that's a WAGO connector, that's high current and then possibly also high voltage. So something can be both high current and high voltage. You're thinking of your net rules. This is what we'll use to automatically lay things out. So at most you need 4 more columns and you include the attributes of given nets. You're going to end up with a bunch of shit that doesn't land in high current, high voltage, or high speed. That's just high density. That's don't care. That's 8 mil or 10 mil traces that are just routing off to a bulk connector. Now, there'll be some number of test points which didn't route to a connector. Maybe 10, maybe 100. And those will, the net name usually gives away what those are. It might be 1.2 volt rail, 3.3 volt rail, 5 volt rail, gate drive. Like, it's just a bunch of errata for doing more validation type tests, not necessarily for doing emulation of next assembly or for doing a HIDL tester. A HIDL tester is focused on connectors. This is a transfer function. There are X number of connectors, and those can be inputs or outputs. And you can draw it as a block diagram transfer function. It doesn't loop around in itself. It has inputs and it has outputs. It might have multiple banks of inputs and outputs. So we scoot all that down in the chart, and we've already made a couple calls to AI just to do that mapping for us. You can hard code it, but we're going to use AI just to use it. And you put some boxes in the top. So percent coverage, all right? This can be calculated as a ratio of the number of test point pins which aren't no connect, meaning they do something and don't have a test point, and then you list them. These are the immediate requests for change that you feed back to the engineer, and that's why this process must take less than 20 minutes, and it can't take 2 hours or 4 hours. It can't be brute force, and it must be repeatable. It has to be script. You can do a pass by those and determine if in fact you're missing something. It could be that some pins are there but not required. Like if you're driving a fan, you need power, ground, and PWM. You don't necessarily need TAC, right? It's nice to have, but it's not required. So sometimes TAC will just be hanging there going nowhere because nobody's reading it, right? No one knew to read it. Maybe it's open collector, you know? Maybe it's duplicate pins that are just there to differentiate one connector size from another. Let's make sure we're driving to the right place and we know where we're going. Okay, so we have our report, and we either have 100% coverage or we don't. If we have 100% coverage, we move forward. If we don't, we issue a report to the engineer saying, hey, look, I need to emulate all these connector interfaces, and these are the connector pins, which with the connector name, the pin number, and the net list. Real fucking clear. And I don't have a test point for it. All right, you feed that back, and you'll get some friction there, some grief, like, oh, it's a tight spot. I couldn't fucking put a test point. You say, all right, well, how the fuck am I going to test it if there's no test point? All right, you have that negotiation. Have the most pleasant person on your team do that negotiation because it draws blood. All right, now we're on to the task at hand. We have all the information we need. There's a couple more columns I didn't tell you about. When you strip out a test point, you get the XY coordinates of it. When you strip out a connector, you don't care. Now, picture a rectangular box. It's wider than it is. So you got right to left, front to back, and top to bottom. So X, Y, and Z axis. It's wide in the X axis. It's it's not as wide in the Y axis, and it's say 6 inches tall. This is the box we're working in. We're going to bisect that box in the middle of the Y, in the middle of the Z. So we have 3 inches going up from Z0. We have 3 inches going down to -3 from Z0. The box is bisected. All right, that's where the PCB lays, and the top is the top. And then there's a bunch of test points, and then now there's a bunch of gold pins right there. And the PCB rides on top. And so what we need to do is build the PCB that goes in the bottom. So you could just, in the CAD model, push that PCB straight down in the Z direction until it's touching the very tippy bottom of the gold pins. And you'll see that each pin goes right through the center of a test pad hole. All right. Now we have to replace each one of those test pads with a via that is larger in diameter than the pin, which is smaller center to center than the pitch, which is 50 mil, which has a minimum annular ring, and which complies to a 2-layer design. So this part of it we'll just do manual. It could be scripted. Basically, you want to strip everything off of the board except for the board outline, the board silkscreen, the test points, the connectors, the net list between the test points and the connectors. So that can be scripted. I'm not going to try to jump the gap on it right now, but you can just do that by programmatically highlighting all of those things and then delete everything else. You're left with the board outline, top and bottom silk, test points, nets, connectors. Okay? Now the trouble is that we have to start mirroring things. So this board, when we push it down in the Z, the connectors, we're assuming connectors are on the top of the board here, right? It's not always the case, but in this case we'll assume that. The connectors are on the top of the board. So when you push them down in the Z, and then you flip the whole box over, they're not accessible. So we need to rotate and flip the connectors. So there's actually a function in PCBA which just says flip the board side of a connector from top to bottom. There's only a top and a bottom of the board. You can't get into the middle. All right, it's 2-layer boards. So we could manually or in a scripted mode flip each connector to be guaranteed on the bottom. So basically you select all on connectors and command move to bottom of board. At this point, all copper is ripped up. We're working only in nets, and every test point is connected to a connector pin. And there's a few test points which are floating around connected to don't cares. They're either high voltage, high current, high speed, or high density. All right. We now have our connectors in the bottom of the board, and we have the original silk. All right. We're going to scrub the silk, and we're going to write on the top of that board, production top. And on the bottom of the board, we're going to write test top. This is to keep your orientation. It will fuck you up bad. Number one most likely spot to make a mistake. If you're a PCB artist, you understand that you get into mirroring issues and flipping issues, and it can really fuck you up. You got to know your colors at top and bottom. You have to silkscreen mark it or you will fuck up. On the bottom, we put clear silkscreen names of every test point, big enough to fucking read, like 12 font, dude. And if it's too tight, fuck. So we got to do our best to mark our test points. You can even put little mappings of constellations of clusters on the side. Do whatever you have to. We're going to mark the test points. We now will pour ground. We had to do a little human interpretation to determine the number of grounds in the circuit. If there's multiple grounds, it's a more complicated task. If there's only one ground, it's an easy task. Pour ground top and bottom. We can use a 4-layer board here, but I would prefer a 2-layer board. And I'm not worried about orphaning grounds. It'll all get tied together, and the next assembly you can't see. We now auto route power and ground to the net rules, to the current requirements, and you can route it manually, you can auto route it, you can assist route it. Just make sure that it's sufficient cross-sectional area to carry the current, and that's burst current, and leave those traces unmasked. That can be automated as well. These are just all steps you run, just clickety, 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 clickety. And in something like Eagle and KiCad, you can actually just take all this off board and take it all back on board again. If it's a different sort of IDE, you might have to work against it. So it could be pretty intensive. I don't know yet. I'm about to do it. We always route our ground first. Get all those landed. Set some rules for minimum, for islanding and minimum ground, net rules. We then route our power. And we might change out that power connector for our own, some Wago 221. Doesn't really matter. That can be solved after the fact with a couple clicks. The next thing we do is we route our high speed. Just have the auto router do it. Same balance pairs, same net rules, whatever they are. And that will pop up. Might be a little bit of manual wrangling to maybe the original high speed connector was vertical. And we might swap it to a horizontal, right? Just thinking about the XYZ of the space we have. And there's some manual work here just to make sure that everything is sane and pointed in the correct direction. Yeah, hypothetically, you don't have to do any changes here, but you should think about doing it. If there's anything proprietary, switch it out to common. USB-A, real simple. Ethernet, real simple. Connectors that are commercially available. We go ahead and route in copper the best we can. So we start with our thick traces, and we set a minimum. It's not going to be 3 mils, dude, like 6 or 8 or 10 mils. And try to route it 10 mils, whatever we can. It's 50 mil on center, and so the hole size we chose for our test points will decide how tight of a fucking route we can get. The ground plane's going to be broken in there. We don't care. That's not the true ground plane. Make sure you can route at least 2 traces away from any pin. And the tighter you make the holes, the harder it is to mechanically affix to the point where it may not affix. And the larger you make the holes, the harder it is to route. So this is where, the same person should be doing the job so they appreciate the trade-off. This is where you really wish you'd put everything on a 100 mil grid instead of a 50 mil grid when it comes time to fucking route that shit away, especially if it's high current and it needs more cross-sectional area. Remember that we can use jumpers. In the old days of 2-layer layout, it was very common to jump something on the board. And so you just iterate the net. Say it's 5 volt net, and you got 5 volt net 1, 5 volt net 2. Well, this is where you've left the board with a jumper to do the impossible, to jump out. And this is what's done on the inner layers. This is what the kids do on inner layers. In the old days, you did that by jumping off the board and landing back on it again. You have to account for that. It's very solvable. It's very easy. In fact, you can jump every single one. If you want to skip the routing step, you can just break out all the connectors to a through hole for, say, 36 gauge bus wire, 42 gauge bus wire, okay? And then you can just go in there like you would if you were wire wrapping and just literally twist bus wire, right? And make your own high-speed signals. Fucking put copper tape over it. That's how it was done in the old days. You were not doing that. And don't worry about it. It's not a speed test. It's just a basic communication test at low speed. So think of it that way. You could just jumper everything. So if you can jumper everything, you can jumper some. Route it out. Take everything that's left over and either splay it out. A good connector is 100 mil space pin headers. So it's just a long row or 2 rows of a common IDE ribbon cable, 100 mil space. All right, so that's so that you can get a heavy enough ribbon cable to run 3 amps if you need to. And break those out. Separate them if they're obvious, so you don't end up with a split ribbon cable. You can replace a ribbon cable with a multi-pin header. These are headers, standard. And you can have those made up with black, blue, and white wires, and you can populate them to suit. You get them in 90 degrees. This is what computers used to be built of. You're now broken out. You can play with the outline of the board to do cutaways. So now you cinch down the outline of the board to be as small as is reasonable to land all your connectors. You can bump and move your connectors, of course, before you lay out copper. Depending on the constellation of test points, you probably won't need all of the footprint of the board. You want to minimize it so that you can reach in underneath and rework. you're going to want holes in the board. Okay? So the board isn't going to be a rectangle or a circle. It's going to be like an octopus. Okay? You're going to have cut-ins on the PCB. This is to allow physical access for inspection, rework, and repair. Any place you can, you cut away the board so you can get in there and work. And just make sure that you hold the board house rules. You might have to have a frame around it to get the board house to handle it. And you can cut that frame off later, or use V-cuts, or use perforations, via perforations, or drill hits. Doesn't matter. Know your board house, know their rules. They can only go so far. This isn't any kind of like flat flex or anything like that, dude. This is a simple 2-layer board in 1 or 2 ounce copper. You gotta print off the documentation of that mapping. Everything has to be on the production top of the board, or on the test top of the board, which is the production bottom. Now that's if you have the production board. Normally you don't. All you have is XY coordinates and a list of connector names. And so you can do that even easier. This is the reverse engineering method of taking the source files. So that way you don't have to go look up the BOM and find the exact connectors for everything. And you don't have to go look up each pin out from the schematic and manually transfer it. It'll give you a day's work if you do it from scratch. Do you understand? I need 20 of those. I need 20 other things too. It's one of those things that nobody sees, nobody appreciates, no one understands. Like 1 in a million people will understand what the fuck I'm talking about. It's frustrating. Well, that's why you highlight it, make the board in purple. Lots of pizzazz.